All right, day 8, we're doing a quick recap of what happened. So remember at the beginning, because we had a quiz 2 coming up, I handed back quiz 1 and I gave people time to look at their quiz 1, to look at their quiz 1 solutions on Blackboard, and to look at the online homework on Blackboard. One of the reasons I did this was because the next day was going to be quiz 2, I believe. Yes, quiz 2. And one of the questions on quiz 2 was the online homework. That's why I wanted to give you time to look at the solutions in class. After that, we had some announcements. On Friday, so the very next day, we'd have quiz 2 in graphs and graphing. We were also going to wrap up chapters 1 and 3. We had 7 important mental shifts in constant rate of change, which are going to be on the first test. And then on Tuesday, because Monday we do not have class, we're going to start with what questions is calculus designed to answer, and start chapter 4, going more in depth into constant rate of change and rates of change. So, shift 7. We want to go from the idea that function notation is an order to do to function notation represents an output. If you remember, on the previous day I had given you f of 2 and I'd said go, and without any more instructions, pretty much everybody did this. F of 2 equals 3, 2 squared plus 5, 2 minus 2, 4, 12, 22, 20. And they got 20. All right, that's not wrong. But this isn't an order to do something any more than 3 plus 5 is an order to do something. 3 plus 5 already represents 8 even before you calculate it out. F of 2 already represents 20, already represents the output, or rather, let me put the dependent value of f when x is 2, without even having to calculate all this. Okay, you can, and it's not wrong, but it's just not necessary. Instead, we want to see this as representational. Of the dependent value of f when x equals 2. So then we went ahead and did some practice with this. I'm going to clear these answers, or these notes. Remember when we talked about what came to mind? It's not that I don't think that you should think about calculating it, all right? So if you thought about calculating it, that's good. If you thought about it representing the value of the dependent variable when the independent variable is 2, that's also good. The shift that I want you to make is not to get rid of this, not to get rid of this idea of calculating. You don't want to get rid of it. But instead, I want you to just switch the order, the priority in which they have in your mind, so that the first thing that comes to mind when you see this is that it represents the value of the function f, dependent value of the function f when the independent variable is 2. And then after that, you can say, oh yeah, if I happen to have a formula, I can calculate it. But that's the second most important thing. Let's do some practice. Given two quantities represented by y and p, suppose that p is a function of y according to this formula. All right, where in the above statement do you see all of the following things? Nope. I gave you some time to do this, so now is the time to pause. All right, let's go over the answers. So the function definition is the entire thing. Z of y, how do you define that? Well, you take y, you cube it, you multiply by 3. You add 8 times that same value of y and you subtract 17. The dependent variable is actually p. The independent variable is y. The function name is z. The function notation is z of y. The rule is this formula, which is useful to have but not necessary for thinking about functions and using function notation. And finally, what's the value of p? It's z of y, right? P equals z of y, which equals this formula. So make sure that you have the different understandings of these different terms. I'm going to clear these notes. Is z equals 3 a valid statement? And can we write this correctly in two other ways? Again, I gave you some time to work in groups, so now is the time to pause. All right. If you imagine, imagine these relationships between the input and the output, and you've probably seen some kind of graph like this, right? 1, 3, 2, 7, 4, 8, 9, and you have these arrows and whatnot. All right. Well, if we imagine that this is the function z of y, where are the different values? Here is where the different values are. See all of these outputs? Those are the p's. See all of these inputs? Those are the y's. Where's z? And this is kind of hard for people because they're like, where is z? When z is clearly here, z is not a variable. Z is not a variable. Remember that it was the name of the function, so it is the name, oops, I'm going to change that color to blue. Z is the name of a relationship between y, the independent value, and p. So here's where z is. Z is the arrows, do you see? Z doesn't have any values. Z doesn't have any numbers attached to it. Z is the relationship that connects the inputs to the outputs. And so because of that, it's really inaccurate to say z equals z3, but we can say, oh, this probably meant the output, so we can say either p equals 3, or we can say z of y equals 3. These are two other ways in which to correctly write what's intended by the statement. And now let's go ahead and practice using function notation in a context. I'm going to clear these notes. All right. T is the time elapsed since a Formula One car began moving. D is the distance in feet traveled by the car since it first started moving. The phrase d is a function of t, which means the value of d is uniquely determined by the value of t. So please take a second if you want to pause to do these first problems. Here are the answers. When you say the phrase d is a function of, or is dependent on, or with respect to, then that says the one that comes after that is the independent quantity. So this is time, and which one is dependent? This is the distance. All right, if we want a function name to represent the distance d at any number of seconds t, then w is the function that will take t in and will spit out w of t, which represents the distance. You want to think about a function machine? Wow. It takes in t, and it spits out w of t, which represents the distance. I'm going to clear these notes to do the next problem. Well, let's see. We can leave it. All right, represent the following using your function notation from 1b. This is not 1a, this is 1b. Take a second. Alright, what is the distance traveled by the car in the first 9 seconds? Well, we can use W of 9 to represent how far it moved in the first 9 seconds. What about from t equals 2 to t equals 5 seconds? Well, here's how far it traveled in the first 5 seconds. Here's how far it traveled in the first 2 seconds, so we have to subtract to see how much it improved. What about the second 4-second time interval? Alright, second 4-second time interval means not from 0 to 4 seconds, but from 4 to 8 seconds. So it would be W of 8 seconds minus W of 4 seconds. The change in distance from the 4th second to the 8th second. And what about the change in distance over any 7-second time interval beginning at time t equals x? Well, we start at t equals x. So here's the distance. Here's the distance at t equals x. What about 7 seconds later? Well, what's the distance? 7 more seconds than x. This is the distance at time equals x plus 7. If we subtract them, we get the change in distance over that 7-second time interval. I'm now going to clear these to do the last set of examples. Alright, and now we want to go the other direction. I will give you an expression and you tell me the value of the meaning. Again, now is the time to pause if you want to do these yourself. Alright, so let's go over these. This is 2 times W of A. So this is twice the distance the car travels in the first A seconds. Because this is how far it traveled in the first A seconds, and this is twice as far. Alright, so this is how far the car traveled in the first C seconds. This is how far the car traveled in the first 8 seconds, so this is the change in distance. So, change in distance from 8 seconds to C seconds. Now what about this one? This is how far the car went in the first 7.5 seconds. This isn't an output though, is it? This isn't a W of something. So that's just subtracting 9 from that. So this is 9 feet less than the distance traveled, oops, sorry, I'm writing over that, in the first 7.5 seconds. This one is the change in distance from 3 seconds to H seconds after that. Right? Here we have the distance at 3 seconds. Here we have the distance at 3 plus H seconds. So H seconds after 3. This one's very similar. This is the change in distance from T seconds to 10 seconds after that. And finally this one, you don't have to worry about right now, okay? It's not Actually, let's go over it. So what's happening here? This is the change in the distance from t seconds to 10 seconds later divided by a change of 10 seconds. So we can say if constant, this is if the car is moving at a constant speed, this is appropriate for test 1, this is the constant rate of change because it is the dy over the dx. And that's where we finished for day 8.